simulation domain, and you have PML here, and PML here, and you have a source. And if you use a periodic boundary condition on the left and right, then this source repeats forever in abstraction. So this is actually indeed a true infinitely wide plane wave. Now we have an infinitely wide plane wave. So if you want to put a scatter, here, then what happens is that this scatter is automatically periodized, so it repeats forever to the left and right. So at the price of creating this infinitely wide plane wave, you have to create a periodic structure. Scatter is also periodized. This is therefore case NP. Now consider the next case, Ni. So we don't. In many cases, we don't want to have infinitely periodic structure. For example, when you calculate this social cross section, you want to have an isolated scatter in an infinite space. And you want to illuminate a plane wave on that isolated scatter. And to simulate an infinite space, you usually put PML. And in fact, we can actually replace periodic boundary condition while maintaining so I'll draw the same figure. So you have PML on top and bottom. And you have a source going upward, and I'm saying that you can actually put PML here. The reason we can do this is that actually this source propagates upward. But the PML observes waves only in the normal direction. Therefore, in this section, section propagates parallel to PML. So it's not observed. So then you still have the plane wave, which is not affected by PML. But when this plane wave hits the scatter, it creates the scattered wave, but that scattered wave is observed by PML. So let me actually show the movie. So I'll first show the first case. So this is the case where you have periodic boundary condition on the left and right. And you can see the perfect plane wave. Right? And then we put a scatterer. It gets scattered. But you can see that the waves coming from the left and right, right? That's from the neighboring scatterers. So that's the effect by using the periodic boundary condition. And I said that we can put PML on the left and right, but for some reason I cannot do that in numerical. I can do that in other simulation software, but what happens in numerical is that something like this. So it is not a plane wave anymore. I think maybe there is some parameters in PML, in numerical, or something like that. I don't know why. I'm not an expert of numerical, so. But let me show you and the results by other simulation tool. So here, I actually put a PML. So before minus 1000 and after 1000 is actually PML. So let me simulate this again. You still maintain the plane wave, right? And then put a scatterer, then then it's hard to see, but actually it is observed, very observed, and there's no wave coming out of, from the left and right. Actually, you can show also the scattered wave only. Then it is more clear. It is not reflected at the boundary, or there's no incoming wave out of the domain.
So you did this by subtracting out the plane wave?
I just subtracted incoming wave from the total wave. So let me know if you figure out how to put PML without distorting plane wave. Yes.
In numerical, how did they get a plane wave to only go in one direction instead of propagating in both directions?
They put two sources that has phase differences.
Oh, okay.
So single line source emits plane wave in both directions, right? So if you shift, if you put another line source below that line source, the previous line source, you can actually adjust the phase so that in one direction you have the constructive interference, and in the other direction you have the destructive interference. And I'll talk about the third case. So if the structure is periodic, we can use the so-called block boundary condition. So by oblique instance, I mean something like this. So you have a source plane, and you want to have this source emit plane waves in this direction. So to achieve this, first you notice that so let's say these are these J points where you put the source should have phase delay. So if this is J naught, then you want to excite this point earlier than this, because the phase. This point has a phase delay, so that phase delay should be this. So the distance between these 2 points in x direction is delta x. So you want to give the phase advance by kx delta x. And at this point, your source should be so you have to give this phase delay, and then you also have to impose the correct boundary condition, which is block boundary condition. So let's look at this layer of E3. Then anyway, this is x and y. At this point, you have hg ns minus f j k, and here you have hg now to update EY here, you want to know the HG here, and if you use periodic boundary condition, then you just assume that this value is the same as this, right? But because we are imposing this whole phase delay, this point so you take the field value at here to evaluate the field value here, but you also take this phase advance or delay into account. That is the block boundary condition. So this is block. So if you give the phase delay along the source line, then the block boundary condition, then you get oblique instance.
So for
Yes.
block boundary conditions, it's not based on the source itself, but it's based on the calculated k vector of any waves in the boundary.
You first need to fix the k vector,
Okay.
and then you put the block boundary condition according to that k vector.
Okay. So what if you had two sources at two different angles and block boundary conditions? What would happen?
Doesn't work.
Okay.
I'll mention something related to that right after this. So maybe that will answer your question. So I'll show you the implementation of the block boundary condition and oblique instance. It is something like this. So yeah, I think this is the correct one. So this is the implementation following what I explained. But one caveat is that so when you implement the block boundary condition, you pick kx, and multiply base factor. But when you have the same kx, you can actually have different k. So plane wave is usually Gaussian pulse. It has many different wavelength components. Therefore, it has many k components. So for this k1, which is omega 1 divided by c, and k2, omega 2 divided by the c, and k3, omega 3 divided by c, they are actually going all different angles. So So you need to choose narrow band. You should use or there's a very cool way to handle this. I don't think this is implemented in numerical, but this is a figure from one paper. So here, the thin line, so this is instant angle and frequency. So the thin line, each of the thin line is actually the instant angle as a function of frequency within a single pulse. So single pulse has many frequencies, but in a single pulse, these frequencies have the instant angles corresponding to this point. And the height is some measurement, like obstruction cross-section or transmission. So this thin line is a measurement by a single pulse, which contains a range of frequency and range of angle, instance angle. You repeat this simulation for many pulses, then you eventually get some surface, and then you take the cross section at a constant instance angle, which is this thick line. Then you get obstruction cross section for a single instance angle over a wide range of frequency. So this is a very cool way to handle this problem, but I'm not sure if this is implemented in numerical. I couldn't find it, but anyway, this is another way to handle this problem.
So numerical, if you have to simulate over a very broad range, I mean, do you suggest then just using a series of Gaussian pulses and just doing like 10 simulations?
Narrowband?
Yeah, to get a broadband result.
At least that's what I saw in numerical documentation.
I see.
Yeah, the documentation said that for narrowband you can ignore the angular range
Okay.
difference. So yeah, but maybe there's a script to handle this kind of problem like this.
Sorry, just going back to this also, I mean, so K is omega 1 over C in free space.